I'm Ian Poole. I'm a Senior Engineer and Sustainability Consultant at Elliott Wood, and today I'll be talking about materials. Specifically, I'll be talking about steel and concrete. These are the materials we use the most, and I've only got 15 minutes. So let's start with steel. Steel can be made basically using two methods. There's the primary method and the secondary method. So primary steel making uses coal and iron that we extract from the earth. It goes through a series of processes and ends up with a basic oxygen furnace, which creates the steel we need in our buildings. Secondary steel, on the other hand, uses scrap. So that steel that's already exists, but has come to its end of life. We sort that and then we put it through an electric arc furnace. That turns it into steel that we need. The numbers on the screen show the carbon intensity, roughly, of those processes. And as you can see, the primary steel making route is much more carbon intensive than secondary steel, something between 5 to 7 times more carbon intensive. So we're in a climate emergency, we need to reduce carbon. It seems like a very easy opportunity for us to use secondary steel, reduce carbon emissions, and solve the problem. However, it's not quite so simple, and that's because we've only got so much scrap. So this graph on the screen shows that, roughly speaking, the scrap input as a percent of total production of steel is only about 30%. And that correlates with the ways we produce steel. So you'll see that secondary production only represents about 20 to 30%, primary making up the rest. And even as we go into the future, as more countries develop and have more scrap output from what they've used previously, we're not going to get a lot of more scrap and a lot more secondary production anytime soon. So that's steel, but what about concrete? So concrete is a more complicated material than steel, but in carbon terms, it's actually quite simple. The majority of emissions associated with concrete are due to the cement, and specifically Portland cement. So we do have some things which can help us reduce carbon in our concrete mixes. These are known as other binders or supplementary cementitious materials, SCMs, and you'll probably have heard fly ash and GGBS. Fly ash being a byproduct of the coal industry and GGBS being a byproduct of the primary steel making process, which I just explained. And when we use these in our mix, we can make carbon reductions. So a 50% GGBS mix can achieve up to a 50% reduction in carbon emissions. Again, this all sounds really promising, but we have the same problem with concrete and cement that we do with steel and the availability of scrap. Sometimes there just aren't enough rocks, and in this case, there aren't enough of these other binders, the fly ash, GGBS, etc. And to give a numerical example of that, cement production globally last year was over 4,000 million tonnes. Of that, only 260 million tonnes was GGBS, so less than 10%. And that's only expected to grow by about 0.1%. So we're in a similar situation with scrap. It's already incentivized and there's not enough of it. And what that means in terms of carbon emissions is that because our demand is still going up, the carbon emissions per tonne of cement produced is actually still going up as well. Essentially, we've only got a certain amount of this low carbon stuff. Everything else has to be produced using Portland cement, which is higher carbon. And with a lot of graphs that you'll see around carbon emissions, it's following a similar trend of we need to significantly reduce quickly, yet we're still going up, which is obviously an issue. So this is all very interesting, but why does it matter? And it matters mainly because of carbon targets. So carbon targets in general are great. It's great that now more projects are aspiring to net zero carbon goals or ambitious embodied carbon targets. And that's thanks largely to a lot of the work that Letty have done, the IStructE through their score system and others. However, it does mean to satisfy clients, we need to meet these targets, and low carbon materials may seem like an easy solution to do that. However, the problem is we've only got so much of those low carbon materials. So if I specify them all on my project, then all it means is another project isn't going to be able to use them. So there's not a net industry gain, even if your carbon emissions for your project look better. And so we reach this issue really where we've got project emissions, which is what we focus on, versus industry emissions, which is what matters. And reducing your project emissions through low carbon materials doesn't actually help in any way towards industry emission. So it's neutral at best. What I've actually seen over the last few years is increasingly that it's having some negative impacts. So I'd just like to talk through some of those concerning trends. I'll start with a quote which I heard at a really big event a few months ago, and this was a structural engineer that said, "We realise that we can make bigger carbon reductions through our specification than in our design." This is obviously concerning, especially in relation to what Eva's just said and the hierarchy on screen. We know that by far the biggest impact we can have is through using our design skills to use less stuff, to design more efficiently. We can do a little bit with the specification, but nowhere near as much as we can through our design. And this is how it normally plays out on a project. So an ambitious embodied carbon target is set, and then that is met by using low carbon materials, and that's used in the calculations in the design. So design is looking good. It looks like it's going to meet the targets. We can tell the client that everything's okay. But there's a real reduced incentive to actually challenge design decisions, do things differently, optimize material use. And so there's that missed opportunity to use less stuff, which is a big issue because it's what engineers are good at. And so what then happens as the project gets to site is that emissions may go up in terms of the actual building compared to what you think you designed. And that's known as the performance gap, which is common term used in operational energy. And I think we're starting to see it a lot now with embodied carbon as well. That can be for numerous reasons. But first and foremost, if we're specifying high amounts of stuff that are in a finite resource, which is in high demand, it's going to push the price up. And the client won't always want to pay that. At the same time, we know that when things get to site, things change. Program might drive some decision making, and all those changes can end up resulting in more emissions. And the green bar there shows what the missed opportunity was. If we designed it better, if we focused more on carbon reductions in the design, then we'd have achieved a better outcome. And thinking forward a bit as well, as more standards and accreditation systems enter the market, increasing emissions may result in loss of marketing potential, missing out on those standards, or higher offsetting payments. So again, that's going to result in an unhappy client. So what's a better way of doing this? So I still say to set an ambitious embodied carbon target, but then use industry average consumption values to guide your design all the way through the design process. This will mean that you select the correct materials, the best materials in the best place. And then it will also drive you to find opportunities to use less, to maximize your skill set as an engineer, and to really challenge the client to make different decisions and better decisions around design. Design out the transfers, the cantilevers, tighten the grids, etc. And then hopefully that means you'll meet your targets and have both a project and an industry benefit. So we must take caution in single-minded approaches that prioritize an individual project over the wider industry benefit. I'd like to just move on now and talk about some specific examples where we can have negative impacts outside of our project. The first few around GGBS. So this is a very valuable binder, and it has been for a long time on large infrastructure projects and in hot climates because it helps to control crack widths. What that allows us to do is essentially use less reinforcement in our designs in those systems, so tunnels, dams, basements, etc. If we start using that GGBS in our buildings where it's not providing us with any performance benefits, it takes that resource away from being used where it's needed. And so on those projects, they'd have to increase their reinforcement. So this therefore means more stuff is used, and we've had a negative industry impact. The next example is, again, sticking with GGBS, is around curing times. So the graphs on the right of the screen there show that basically as we increase the amount of GGBS in our mixers, the amount of time it takes for that mix to gain its strength increases. So really, GGBS is very incompatible with early age strength requirements. If we do need early age strength and we put a lot of GGBS in our mix, we basically have to over-design that mix, put a lot more total binder content in to achieve the strength at short-term gain, and then that concrete will then be much stronger than we've actually designed it for. So we've wasted material, we've used more stuff. The next example is around transport emissions, and this applies to both steel and concrete. So with steel, we basically in the UK produce much less than we need. We then export half of it and then import about twice as much as we export. So in doing that, we're releasing a lot of carbon into the atmosphere through transport, which isn't strictly necessary. In In the case of GGBS, it's actually a bit worse in that in our calculations, we actually assume that the GGBS is sourced from Belgium. So this is baked into the A1 to A3 value that you'll use if you use the IStructE tool or the ICE database. But we know that we import GGBS from as far as Japan, which is basically on the other side of the world. And when we do so, there's an 8-fold increase in emissions. So more transport emissions, more fuel, more stuff is used. And the final example I wanted to talk through is with steel. I mentioned at the start of my presentation that we have primary and secondary produced steel. Now, in theory, these can both be used to make any product that we need, but the reality of the industry is that secondary steel production is used predominantly to produce reinforcement and some open section steel. And what that's led to in the last few years is that there's been a shift away from using plated steel, which is typically only produced using the primary method, to using more section, because then we can specify secondary steel, get the carbon gain associated with that, and the carbon looks good on our project. That's really damaging if that change has resulted in more material being used. All that secondary steel is going to be used across the industry anyway. So if you can make savings in your design through using plated steel, then it's going to have a net industry benefit. As you can see on the graph there, we reduce the amount of primary steel that we need. All the secondary steel is still produced, it's just used elsewhere. So other people essentially benefit from your decision. So finally, what can we do? So there are things we can do with materials to have a positive impact and put that into our specification. So there's been a lot of amazing work done by SteelZero and Responsible Steel over the last few years to create the graph that you see on screen, which is basically the carbon intensity of steel making across the world based on the scrap input. And you can see there's a linear trend there. So instead of specifying a certain production route or amount of scrap input, if you simply specify that across the project, the average carbon intensity of your steel must be below the line based on the scrap input, then that'll have a much more significant benefit to industry. You can help ratchet that down and accelerate towards net zero. Going on to concrete, and there's a similar initiative that's being carried out by the Low Carbon Concrete Group over the last year. And they've produced the graph on the screen, which shows carbon emissions against strength class on the x-axis. Unfortunately, this graph doesn't take into account the specific mix. So as you can see on screen there, if I specify in my projects that every concrete mix has to achieve an A grade, all I'm doing is basically saying that about 70% GGBS has to be used, which, as I've said, isn't really the solution. So you do have to tailor this to your mix. So how I'd recommend doing this is if you've got, say, 25% GGBS as your standard requirement on the project, you could specify for those mixes that an average of D or maybe C has to be achieved. And if you have got any places where you're using a higher mix for whatever reason, then adjust the banding accordingly. So a 50% GGBS, maybe specify B or A. So the question I always ask myself and try to use to guide design decisions is to ask, is the decision you're making helping to use less stuff at an industry level? And if it's not, is it at least helping to unlock new low carbon stuff? And I think this is a good thing to have in mind in general throughout our design process.
Ian, you have 1 more minute.
Thanks, Arno. I mentioned that there's a lot of disadvantages to specifying low carbon materials, but I do have to cover the other side of the argument. So what are the advantages? And for me, there's threefold. The first one I've already mentioned, if the specification reduces total material use, then that's a good thing, and we should definitely be using it in those cases. The second is where losses now may result in future gains. This is a lot more complicated, but a good example of this is with AACMs, where we've got a new technology, it's inefficient now, it's not currently having a positive benefit, but it may do in the future. And finally, there may be opportunities in your region to increase low carbon supply. A good example of this is with fly ash, where I think there is a bit more to be used than we currently use. So if you're in a region where there's a lot of coal making, then specifying more fly ash kind of makes sense. So finally, I think our job as engineers in the climate emergency is to provide what society needs. And that's not necessarily what it wants or just because we can, but what actually gives value to society with as little material as possible. If we use as little material as possible, we'll decarbonize more quickly, and we'll reach net zero quicker with lower total emissions, which will benefit everyone and everything on the planet.